Hello and welcome to this video tutorial. In this tutorial, I'm going to talk about most widely used assembly instruction in this course. We start with the copy instruction. So when you want to copy data from one location to another location, you will use move command. Move basically copy the data from source to destination without removing data from the source. So the source data gonna stay the same, but the destination gonna be having the same data as the source. So in here, we have a numerical example where we moving 10 to or copying 10 to EAX register. In the second instruction, we copy data from a memory location with address 2000 into EAX register. So as mentioned, the content of the memory at location 2000 won't change. We only copy that data to EAX register to use in our assembly code. In here we have some arithmetic operation instruction. So we have add instruction and subtract instruction, multiplication instruction, division, increment, and decrement instruction. In addition or in add instruction, we add the source to destination, source and destination, and then we move the result to destination register. And then we have subtract instruction where we take the destination, subtract the value of the source from it, and put the result in the destination register. And then we have multiplication operation, which has the argument of reg. Reg could be a memory location or could be a register in our CPU, one of the general purpose registers in the CPU. So as you can see, mul has only one argument in here, but implicitly it works on EAX and EDX register as shown in here. So your argument reg is going to be multiplied by the content of the EAX register, and the result is going to be placed in EDX concatenated with EAX register. The reason that we do this is because the result of the multiplication always has a longer length than each of the argument of the multiplication. Here EAX is 32 bits. It's going to be multiplied by register value of 16 or 32 bit, and the result is going to be placed in a concatenation of EDX and EX register, which is 64-bit space. Then we have the division operation. Division operation, we also have one argument, but the syntax implicitly works with EDX and EAX register. So as you can see in here, the quotient gonna be placed in EAX register. And the way that the instruction works, it takes the content of EDX concatenated with EAX register, divided by the reg, and then put the result in EAX register. For the remainder, we also take the value of the EDX concatenated with EAX, we divide it by reg, and take the modulo of that and put the result in EDX register. Basically, we have the remainder value stored in EDX register and our quotient stored in EAX register. Then we have increment and decrement instructions. This is similar to the one in C. So basically you increment the destination. So if the value of, for example, EAX register is 20, and then you use increment EAX, then the value is going to be 21. And then if you use decrement destination, for example, and it's work on, so here is the example, and it's work on, for example, can work on the memory location or can work on the register. So in here we have an example of a memory address with a length of 16 bits, and we say, okay, the content of this memory should be decremented by reduced by 1. So it reduced the value and then update the content of the address 1000 in the memory. So I forgot to mention this command over here. So reg argument in here could be a register or could be the location in the memory. So in this example, mul is going to work with ESI register, meaning that we take the value of EAX register in here, then we multiply it with ESI, and then we put the result in EDX concatenated with EAX register. In here, we have div EDI, meaning that we take the EDX concatenated with EAX register and then divide that value with the EDI register and then put the quotient in EAX register and put the remainder in EDX register. One thing to note is that we have the signed equivalent of this instruction as well. So the signed equivalent are imul and idiff. You will see more detail about this instruction in the coming lectures. Then we are having the function called in our assembly. So to call a function, we use call label. So label serve as the name of the function normally in assembly. If you want to make a resemblance with C, so you can say call my function. So once you do this, then the value of the EIP register gonna be pushed into the stack, and the control of the program gonna go to the place in our code which is specified by the label. Then we have return argument. Basically, return, we use this keyword at the end of this function. So when we use return, then the value of the EIP register from the stack gonna be pop out. I mean, one of the value in the stack gonna be pop into EIP register, and the control of the program gonna go to that line specified by EIP register. Therefore, the program will return to where it was before the function call. The next syntax is push item. Push item basically placed the value of the item to the stack. The item could be a constant value or could be a register. So once you say push a register, for example, EAX, it's gonna save the value of the EAX. If this is your stack, it's gonna save the value of EAX into the stack like that. And then you also can push a number into the stack. In this case, we have 32, and we wanted that to occupy like 4 bytes or 32 bits. So then you push, for example, 32 in the stack. And then we have pop with arguments like this. And once you use pop, then your argument has to be registered. So you basically take the value that is stored in the stack and you put it in EAX, you put it in your argument. For example, in here we have EAX register. So when we say pop EAX, it's gonna take the top element in the stack into EAX register. So for this example, it's gonna be the value of 32. Okay, let's move on to the next. So we have here bitwise operation. Bitwise operation normally works on like logical operation like AND, OR, XOR, shift left and shift right operation. So let's take a look at these operations, see how we can implement them in assembly. These instructions gonna be similar to the math operation we saw in the previous section. So again, we have source and destination. For AND operation, we take the destination and the source, we AND the result and put it in the destination argument. In here, we have OR operation. We take the destination, we OR it with source, and we put the result in destination. So it is bitwise, meaning that if your source is, for example, 1, 0, 1, 0, and your destination is 0, 0, 0, 1, and if you do the OR operation, then you get 1, 0, gonna be 1, 0, 1, gonna be 1, 0, or with 0, gonna be 0, 0, or with 1, gonna be 1. So that's the reason it's called bitwise. You do the OR operation on each of these pair of bits, and then you take the result, you put it in your destination register. Could be register or could be a place in the memory. All right, then we have XOR operation is the same. You take the source and then you XOR it with destination and put the result in the destination again. Then we have shift left, then destination count, meaning that you have your destination register, you shift it to the left with the value of count and put the result in the destination register. For example, in here, we have EAX2, meaning that whatever value stored in your EAX register, 1, 0, 1, and like that, you shift it as much as 2 bits, because 2 is specified in here. Basically, 1 gonna go out, and then 0 gonna go out, and then whatever value you have in here gonna be shifted to the left, and the first 2 bits from the left gonna be populated with 0 value. It is as simple as that. All right, then we have shift right operation. When you have your destination, then it's gonna be shifted to the right as much as the count value or second argument in here. So we have an example in here where we wanted to shift that value to the right with 4 bits. So we have the EAX register. So we have a value stored in a memory which it address it is in EAX register. Now we want to basically shift right that value that its address is specified by EAX register as much as 4. So we do that. So basically we take that value, we shift it to the right with 4 bits, as much as 4 bits, and then we for those 4 bits that shifted to the right, we basically put 0 in here, and whatever value was previously in here gonna each shifted by 4 bits to the right. Basically shift to the right, each shift to the right gonna divide the value of that register or memory location by 2. If you shift this by 4 bits, it means that you basically divide that value by 2 to the power 4. I forgot to tell you about the shift left. So when you do shift left, you basically multiply the content of that register or memory location by 2 to the power of amount of shift. So for this example, you basically multiply the content of the EAX register by 2 to the power 2. So we are going to see the signed version of the shift left and shift right also in coming lecture. So the equivalent is SAL for arithmetic shift left and SAR arithmetic shift right, which also consider the sign bits in the shifting process. SAL is similar to shift left, so they are just alias of each other. So there is nothing technically different between SAL and SHL. But SAR, they are different. When you do the shift right for a negative number, then basically you populate the bits from the right with 1. So you keep the sign bit as it was in the original value of that register. That's the only difference. So you're going to be seeing more example in coming videos. All right, then we have conditional and jump instruction. So then we have comp B and A. Basically, you subtract A from B, and then based on that, all the flag registers gonna be impacted. Then based on the flag register, then you can use jump instruction to go to the label specified by that jump. In here we have an example. Comp EAX with 0. Basically, it's gonna be subtract the value of EAX from 0. If the result is 0, then you can use, for example, jump equal to go to the end loop, which is a label in your program. So in here, we say jump equal label means that when the value of B is equal to A, then you jump to that label. Jump not equal label means that if B is not equal to A, then you go to the label. Then we have jump greater or equal, jump less than or equal. Then you go to a label. And these are the conditions which we can use. We then have test instruction where it is a bitwise and between the register value and that immediate value, and then by doing this operation, then the sign flag, zero flag, and parity flag are going to modify while the result of the AND operation is going to be discarded. Basically, you use this test to AND the value of the register with the second operand, and then take a look at these three flags and decide where to go after that. That's the reason then you can use jump 0 or jump not 0 instruction after the instruction. For example, in here, we have test EAX with the value FFFF, meaning that we want to know if the first 16-bit of the EAX register, their AND gonna be 0 or not. So if the result is 0, then we know that the first 16 bits are 0, and therefore we use jump 0 instruction to jump to the label accordingly. So the most important thing to note is that the result of the EAX register won't change after this syntax. This act as like AND, but it doesn't change the destination register. And sometimes this is necessary for us, and it's going to save some space using AND, not changing the destination register. Then we have jump 0 label, jump not 0 label. It means that if the previous instruction, the result was 0, then you jump to the label. If the previous instruction, the result not 0, then you jump. Then we have unconditional relative jump, and then we have unconditional absolute jump. In here, you basically gonna be jumping to the label, but in here you jump to a instruction where its address is specified by EAX register. These are some two miscellaneous assembly syntax where we are not going to use much in this course. So the first one is no op operation, where basically when you insert this operation in your assembly code, none of the register except EIP is going to be impacted, and the result of your program is not going to change. The only thing that this creates is delay and some space within the memory. Some of the applications that you write assembly for, they might need delay, for example, to create pulses, right? Therefore, this syntax is going to be useful in those kind of situations. And then the other syntax that we have in here is the halt syntax. Basically, this halt syntax halt the CPU. So it's just halt the CPU, and then your program waits to receive an interrupt from your peripheral or from software to continue its operation. We have some information also over here. It explains that this register in x86 architecture are 32-bit. This register are 16-bit, and this register are 8-bit. Then we also have fixed addresses where we have a bracket around this address, and you might use this in your syntax when you are copying something from somewhere to from one location to another location in the memory. Then we have a notion of dynamic address where the address is specified by one of the general purpose register in the hardware. Here is end of this video tutorial. See you on the next video.